Hello student, to the Foundation of Classical Electrodynamics course. Under module 3, today we have lecture number 54, and today we will going to discuss more about the magnetic vector potential that we started in the last class. So, today we have class number 54, and our topic today is magnetic vector potential. We will continue this discussion that we started last class. So, we know that the divergence of B is equal to 0. Since divergence of B equal to 0, from that we can write B as a curl of a vector function, say A, and this vector function A is termed as magnetic vector potential. Now, this magnetic vector potential, because if you go back to again the Helmholtz theorem, I have done this several times, that divergence of B is equal to 0 and curl of B is mu 0 j. These two information, if these two informations are known, then I can able to write B as a function of A in this way, where curl of A gives me the B, where A can be determined as, according to the Helmholtz theorem, as 1 by 4 pi integration and divided by r minus r prime, and here I should use the expression of curl cross B in prime frame. Better to write B as a function of r prime. With dv prime, and from that I can simply write that this quantity is 1 by 4 pi mu 0 I can take outside, because curl cross these things is nothing but mu 0 j. So, it should be like integration of j r prime and r minus r prime dv prime. So, this we derived last day. Next, the question was the uniqueness of A. Next, the thing that we discuss, that is A, the vector function that we are talking about, is unique, and the answer is no, because you can form a vector function A prime. Suppose A is given, A as a function of is given, and you can construct another function A prime R using the given function A in this way, that gradient of a scalar field R, then A and A prime both leads to the same B. So, from here we can write that curl of A will give the B, and that is the same quantity that curl of A prime so this will give rise to 1b and this will again give rise to the same b, where A and A prime are different quantity. Okay, that was the discussion we had in the last class. So, I quickly recap. Now, today we are going to impose certain constant. So, that is the thing. So, we impose now a constant on the vector potential and that constant is called the Coulomb gauge. So, what is the meaning of constant? I will discuss. So, that constant is eventually the Coulomb gauge. This is called Coulomb gauge constant. Coulomb gauge constant. So, what is that constant? The constant is the divergence of A has to be 0. That is the constant that I impose. It is not necessarily that the vector potential that is given for which I am going to calculate the magnetic field should have this property that if I make a divergence of over that vector potential, it gives to 0, but we put a constant over that we want that A in such a way that if I make a divergence over A, it should be 0. Now, as I mentioned, it is not always true that this is not always a valid constant. So, suppose the divergence of A is not equal to 0, okay, because the Coulomb gauge constant we need to put, but A is given for which the divergence is not equal to 0. That means, simply the A is not satisfying this equation, whatever the equation we are having, it is not satisfying. But we know that there is no such uniqueness over A. I can construct my A in a different way that I discussed in the last day. Today also I mentioned it. So, what we do that since it is not equal to 0, then we can make it 0. We can have another A prime. Obviously, that A prime can also produces the same B. This is my new vector potential, and that is this we know by mathematical form. This is the form, and demand that I construct A prime in such a way that we demand that the divergence of A is 0. Okay. So, if divergence of A is 0, from this equation what I can see that if I make the divergence of A both the side and keep this equal to 0, then eventually we have divergence of A plus divergence of right hand side. I am just writing chi is equal to 0, or grad square psi, this is a vector field, is equal to minus of this. So, that means in order to make A prime divergence of A prime 0, in order to make divergence of A prime 0, what we need to do is that the chi should satisfy this equation, and this is nothing but the Poisson equation. This is whose solution is known, right. So, let me write it down once again. So, that means the chi which we have a freedom to choose should satisfy these Poisson equation in order to hold the Coulomb gauge. So, it is like it should satisfy this equation, and this is equivalent to, now if I want to write it a equivalent equation here. So, this is equivalent to in electrostatic, which is known, which is a known equation. So, let me write it down and then we are going to compare this. So, in electrostatic we already had a equation like this, right. The okay, let me write it properly. Square this is equal to minus of rho by epsilon 0. That is our usual Poisson equation in that for the potential that we had for electrostatic, and whose solution is known, right. And the solution phi was 1 by 4 pi epsilon naught, then integration of rho dV prime divided by curl R. Here also, since the solution is this is a volume integral. So, these two equations are identical. So, I can readily have the solution, and the solution for psi is simply, if I want to find out the solution here, I can write this. This is nothing but 1 by 4 pi, and then integration of this quantity, over R dV prime. Okay. So, under Coulomb gauge, these I can make my A prime to I can satisfy, I can prepare my, I can construct my A prime in such a way that it satisfies this equation, which is the condition for Coulomb gauge. And in order to satisfy this equation, I need to choose my scalar field chi in such a way that this is the solution, this is the way I need to choose, because this divergence of A, which is non-zero, is given. So, these things is given, this is given. So, exploiting that information, I can construct the thing. So, this is given and this is not 0, that is the condition we start with, that suppose these things is not 0. So, this is not 0, some value is there. So, that thing I will put here, plug it, and then find out my chi, and then I construct A prime that should satisfy the Coulomb gauge. Now, if the Coulomb gauge is there, what we get? Let us check what should be the expression of A then. So, under Coulomb gauge, under Coulomb gauge, what we have? We have divergence of A is 0. We have divergence of A is 0. Divergence of A is 0. This, from this information, I can have curl cross B is equal to mu 0 j, and then curl cross B, I am making curl of both the side, that sorry, I should write this is A. I do not want to make curl of both the side now. So, from this equation I write, because B is curl cross A, and I just replace B here, and that thing should be mu 0 j. Now, curl cross A, we know this is a very famous identity, we did it during the vector calculus, and it is simply the minus of grad square A plus vector A plus the gradient of the divergence of A, and that thing should be equal to mu 0 j. Now, here we had this condition divergence of A, which should be 0 under Coulomb gauge. Under Coulomb gauge, right. So, this should be 0. So, then we simply have a Poisson equation, a vector Poisson equation, which is grad square A, which is a vector quantity, is equal to minus of mu 0 j. This is nothing but a Poisson equation, but vectorial form. So, this is a vector Poisson equation. Okay. So, now from that, if I want to extract the value of the A, the solution is simply mu 0 divided by 4 pi, because his solution is already there written, right, the solution of the Poisson equation, and then j at some r prime dv prime whole divided by r minus r prime. This is some volume integral over the entire volume V, and that thing for volume current density. So, for surface and line current density, we can also have a expression. In some places we may require that. So, for line and surface current, for line and surface current we can have A is mu 0 divided by 4 pi, then integration I current dl and say dl prime, and then r minus r prime, and I can if for a steady current we know that, then I can take I outside. So, this is simply mu 0 I by 4 pi and then integration dl prime and r minus r prime. So, this is for line current, and for surface current the vector potential can be written like mu 0 divided by 4 pi surface current density K prime d A prime divided by r minus r prime. So, that will be over surface, that will be over line, and previously the expression is over volume. So, these are the three forms for current density, different current density or different current, line, surface and volume current, and that is the expression for the vector potential A. Now, after having that, let us now calculate few cases where how to calculate the current density for different cases, how to calculate the vector potential. So, calculation of vector potential A in a few simple cases. Few simple cases we are going to calculate. So, the first thing, for the first case we calculate is a straight current carrying wire. A straight current carrying wire. So, let me draw the current carrying wire first. Suppose I have a straight wire like this, and the current that is flowing through is I, and I want to say find out the vector potential at some point here at a distance r, because some magnetic field should be here because of the flowing of the current through this wire, and as a result we should have some vector potential A. So, that we are going to calculate. So, so from here to here, this is say this is say r vector, and from here to here, so this is dl section, and this is say the length is say minus L to plus L, and this is our origin. So, I can use this expression, my A should be at r should be mu 0 I divided by 4 pi integration minus L to plus L, and then the current is flowing along this direction, and that is say if this is z direction. So, z unit vector dz divided by r square plus z square to the power half. So, r square z square is simply this one, and since it is z direction, so simply we have d l vector is z unit vector dz, considering the wire is over this z axis. Okay. So, I simply now evaluate this integral, that is all, and if I do this, then this is z unit vector, then mu 0 I divided by 4 pi, and it should be ln, because this is, we know, z plus root over of r square plus z square, and evaluated at minus L to plus L. Okay. So, so if I evaluate that, so my A should be, okay, my A should be A is z unit vector mu 0 I divided by 4 pi, and this is simply ln. I just put the value of this boundary value. So, it should be L plus root over of r square plus L square divided by minus of L plus root over of r square plus L r square plus L square. That is the value. Okay. Now, if the wire is very long, so for a very long wire, the condition simply when R divided by L, this ratio is very less than 1. That means I try to find out the vector potential as a distance r, but that distance should be much smaller than the distance of the length of the wire itself. So, that is the condition here, and if I put this condition under the limit that this is very small, we can simplify the expression a bit, we can approximate the expression a bit. So, A is simply z unit vector, then mu 0 I divided by 4 pi, and then I have ln and take L common. So, it should be 1 plus r square divided by L square whole to the power half, and in a denominator we have minus 1 plus 1 plus r square divided by L square whole to the power half, and then we make a binomial series kind of expansion of this quantity that simply leads to z mu 0 I divided by 4 pi, and then ln 2 plus half of r square divided by L square divided by half of r square divided by L square. Please note, I can't neglect r square divided by L square, then we can't do this, because then we have a undetermined quantity. So, we need to just make a binomial expansion here, and then further simplification leads to z mu naught I divided by 4 pi, and then ln, and then 4 of L square divided by r square plus 1, just divide everything, and that is again simplify as z mu 0 I divided by 2 pi and ln 2 L divided by R, because L divided by R is much greater than 1. So, I can neglect this 1 and I can simply write this as a square, and these 2 can come out and we are going to get this. Now, this is the expression we are getting. Finally, my A should be this one. Now, if I want to extract my B out of this A, so what should be my B? My B is curl of A, and A is there, A is there. So, I can simply have, if I execute it, 1 divided by R, because mind it, A is in polar coordinates. I need to write everything in polar coordinate or in cylindrical coordinate at least. So, it should be R unit vector, then R phi unit vector and Z unit vector in cylindrical coordinates. So, I need to exploit this at R phi Z, because A is in this way, written in this way. So, this is del R, this is del phi, and this is del Z, and we have 0 0 and A Z, because only Z component is there, which is a function of R. That is all, because this is only the direction of the A is along Z. Now, this value, most of the terms are 0. So, only we have minus of, if I execute, minus of phi del A Z del R, and that if I execute, because A Z I know this is the quantity, and if I make a derivative with respect to R, then simply I have minus of phi then del R, and whatever the A Z I am having, I am writing this mu 0 I divided by 2 pi, then ln 2 L divided by R, and this value is simply phi unit vector mu 0 I divided by 2 pi R. So, this is the value I have, because if I write this ln to ln 2, so this I can write it as ln 2L minus ln R. So, ln 2L is a constant. So, this will going to cancel out, and ln R should be 1 by R, and this negative sign will going to absorb here. So, that is why I will going to get this result. But if you look carefully, this result we already have. So, this is a known result, right, because we already derived in earlier class that what should be the magnetic field for a wire, infinitely extended wire and or very long wire, and the result was mu 0 I divided by 2 pi, the length, the distance, that is R. So, this result we again rederive, but this time in a different way. This time we are not using the Biot-Savart law, we are not using the Ampere's law. We just use the expression, this expression, to figure out B, and here A is the value, A is the value for A is the value that we basically calculated here. So, this is the way we calculate A, and that from that we calculate B. So, let us do another problem. So, problem 2, we calculate, find A inside A long cylinder carrying a current density J. So, long cylinder is there and it is carrying a current density J, and I want to find out. So, that is the cylinder. Suppose this is the axis, and the radius is say A, and the current density that is given. So, suppose this is J vector. So, I need to find out the value of A, that is the vector potential. So, curl of B is mu 0 J, and curl of A, B is curl of A. So, I just put this is simply mu 0 J. I am writing the Poisson equation once again. So, that leads to A is equal to minus of mu 0 J under this Coulomb gauge, where divergence of A is 0 under Coulomb gauge. So, now J is J unit vector Z, and that basically leads to, because J and A should be same direction here from this equation that we understand. So, A should be, the vector A should be having no x component, no y component, only the z component, and that is Az, because this, from this equation we can say that A and J should be in same direction. Now, using the cylindrical coordinate, so and exploiting this equation in cylindrical coordinate, what we can get is this. So, 1 over rho and then del rho and then Az del rho should be minus of mu 0 J. I am just writing only the rho part because other components are not there. So, I have then del rho and then rho del Az del rho is equal to minus of mu 0 J rho, or rho del Az, a partial differential equation we are solving now. It should be minus of mu 0 J rho square divided by 2 and then plus C. C is the integration constant. Further, del Az, our aim is to find out Az, del rho is equal to minus of mu 0 J, 1 rho is going to cancel out. So, rho divided by 2 plus C divided by rho. Again, if I integrate, then Az simply comes out to be minus of 1 by say 4 and mu 0, then j, then rho square, then plus c ln rho plus d. Now, C a dear constant which can be evaluated by exploiting the boundary condition, and the boundary condition suggests that we have a ln rho term, and that means if I want to find out something in the axis, then rho tends to 0. So, under rho tends to 0, Az should be finite, but here we can see that this term can have a undefined quantity. So, that means the C is 0. So, when rho is less than A, the ln rho term should vanish. Or rho tends to 0, this term should vanish. Under that condition, I can write that A z, which is a function of rho, should be minus of 1 by 4, then mu 0 j rho square plus d. Rho is less than equal to A. Inside that I want to find, right. Now, J is, what is J? J is the amount of current flow per area here. So, I should write I divided by pi A square. A is given in the problem because the radius is A, that is known. So, in terms of that, I can simply have Az to be minus of mu 0 I divided by 4 pi A square. I just replace j here and then rho square and then rho square plus the constant d, if I write and without, so plus some constant d. From that expression I can also figure out my b. B of rho is equal to minus of del rho of Az with phi unit vector, and that quantity simply become mu 0 I divided by 2 pi rho divided by A square phi unit vector for rho less than equal to A. So, I figure out my A, I also figure out from A, I also figure out the magnetic field for this cylindrical system which carries a current I. So, this is the way. So, I just give two different examples to find out A. Now, I should stop because I do not have that much of time to continue. So, in the next class what we do, that we will discuss more about the magnetic vector potential and then try to understand if a current carrying wire is placed, then how it is producing some magnetic vector potential, and again like scalar potential we can have a multiple expansion and how the dipole moment term, magnetic dipole moment come appear, etc. So, with that note I would like to conclude here. So, please try to practice few problems regarding calculating the magnetic field through A. So, first you need to calculate A the way I discussed. So, for a given system having the symmetry, use the symmetry and find out the value of the magnetic vector potential, and then from that calculate the value of the magnetic field B. So, thank you very much. See you in the next class.